Hi, everyone. Welcome back from spring break. I hope that you're healthy and adjusting to the new normal. We're going to talk about simple harmonic motion today. This is an independent learning assignment, and you're going to listen to a PowerPoint presentation with me speaking, and then you'll do a worksheet with some problems, and then the next time I see you will be on a Zoom lecture so we can speak face to face, virtually, kind of. Anyway, we're going to talk about waves during fourth quarter. Fourth quarter is some of my favorite topics in all of physics. All kinds of waves, water waves, sound waves, light waves. And we're going to today lay the groundwork with simple harmonic motion. So here's an example of simple harmonic motion, a pendulum going back and forth. And another example of simple harmonic motion is to put a mass on the end of a spring, a little slinky, up and down, back and forth, simple harmonic motion. So let's do some definitions. So a cycle is a cycle is one complete vibration. So when we were doing the circular motion unit, a cycle was one time around a circle. So from the starting position through all the other positions and back to the starting position. Period is the time for one complete cycle, and the unit would be seconds. Frequency is the number of cycles every second. And so if you remember, the metric unit of frequency is the hertz. And period is the inverse of frequency. Frequency is the inverse of period. Equilibrium position is just like it sounds like. So let's say that let's say that this is my cord. So this is a pendulum, and when it swings down to here, this is the equilibrium position, and then going up to its highest height, from equilibrium to the highest height, that's the maximum displacement of an object from its equilibrium position. So from here to here is the amplitude, and from here to here on the other side is also the amplitude. So let's pretend like we can actually see this mass on the end of a spring going up and down and up and down. So right here, this is equilibrium. This is the amplitude when it goes to the highest point. Then it goes back through equilibrium and goes down to the lowest point. That's the amplitude. Now, if we were to spread that out as a function of time, you would have a transverse wave, looking at all of these positions. So this simulation relates simple harmonic motion to transverse waves and to circular motion. So you could imagine each one of these blue dots is moving in uniform circular motion. Now what I'm going to do is I'm going to rotate this circle on its axis 90 degrees, and we're just going to look at one of the points. This also looks like a pendulum, going back and forth, and you could calculate the amount of time that it takes to go to the left and back again to the right. That would be one complete cycle. And if you were to spread that out in space, because that's what a transverse wave is. A transverse wave is a vibration that is perpetrated through space. So here we go. We're going to spread that out in space. All right, let's do one simple harmonic motion practice problem, and then you can try the attached worksheet to this Canvas assignment. A pendulum swings back to its starting position 5 times during the 10 seconds after its release from rest. The pendulum swings 8 centimeters from its release point to the amplitude position on the other side before swinging back. What is the pendulum's period? So period T is equal to seconds divided by cycle. So that was 10 seconds in five cycles. So that meant it took the pendulum 2 seconds to get from its highest amplitude to its other highest amplitude and back again. So frequency is equal to cycles per second. So the frequency was 5 cycles in 10 seconds. So that would be 1/2, which is 0.5 hertz, because the metric unit of frequency is the hertz. What is the amplitude of the pendulum swing? So the pendulum, like let's say that this is the fulcrum. Oops, hold on. So let's say that this is the pendulum here, and then it goes down to here. This would be an amplitude, and this would be the equilibrium position, and this would be the amplitude on the other side of the pendulum. So from here all the way to here, that would be 8 centimeters. So the amplitude would be 4 centimeters, and another 4 centimeters on the other side when my writing's not good. But anyway, the amplitude would be 8 divided by 2, which is equal to 4 centimeters. All right, everyone. Thank you for listening, and good luck with the problems. And I'll see the morning classes on Wednesday and my 7th period afternoon class on Thursday. Take good care. Bye.